Oh, really? Sorry about that.
Hey guys, you want to start? You want to take a seat? So just a few quick announcements. This Thursday we have a meetup on self-service exploration with Apache Bro. It's going to be on in Diversify in El Segundo. So hopefully we'll see quite a few of them. Next week is Hadoop World. How many of you will be attending Hadoop World? Couple of guys, okay. So we should meet up at Hadoop World too. We can, meet up and discuss some new features and talk about some new things in Hadoop World. Next, I would like to invite Becky from Cross Campus. She's going to give us a short discussion on Cross Campus and what to do over here.
Hi everybody, I am Becky from Cross Campus, as Subash said, and I wanted to welcome all of you here tonight. Thank you for being here and being part of our community. Events is a big part of what we do here, bringing outside community here to be a hub of innovation and creativity and education for everyone in the startup and entrepreneurial community here. But we have our own community, which is made up of entrepreneurs and creatives within these walls. So we welcome you tonight. Thank you for being part of our community, and we are about to launch our second location in Pasadena, connecting Silicon Beach to the east side. So if that's your part of the world, we welcome you to come visit us over there as well and be part of that too. So thank you for Subash to continuing to organize these meetups, and have a great evening.
Thanks, Becky and Cross Campus. Now I'd like to invite a sponsor, WANDisco. Mark will come and just give a short talk about what WANDisco is before we start with the presentation.
Hey guys, how's everyone doing? Mark Harrison of WANDisco. So we'll be doing a little meetup tonight, talking a little bit about how to make Hadoop enterprise ready. So we don't know WANDisco. We're about an 8-man-year-old company. Our little core technology is a replication, focused on open source systems like Subversion, Git, and today we'll be talking about how we make Hadoop enterprise ready through our core replication technology. So just a real quick thanks to Subash and thanks to Cross Campus LA for hosting us tonight. I look forward to educating us. That's good. Alex Pierce is going going to introduce Alex. He's one of our senior big data architects. He's going to be walking through how to make nonstop Hadoop.
All right, you hear me fine? Good. All right, so I'm talking today about WANDisco support technology and how we make Hadoop enterprise ready, and what it really means to be an enterprise ready Hadoop system. Just a couple of quick seconds of WANDisco background. So WANDisco, the name actually stands for Wide Area Network Distributed Computing. That's what our core competency, our core technologies are based around. As Mark mentioned, we are leaders in the subversion space and also in Git replication. And we are actually a public company. We went public a couple of years ago in London, globally spaced out. So, in terms, just throw a quick customer slide, we do have approximately 300 of the Fortune 500 companies who use our technology. Most of this is in the SCM space, as mentioned earlier, but the Hadoop space is growing. So really quickly, what is nonstop Hadoop? That's something I'm talking about today. Nonstop Hadoop is a non-intrusive plugin that provides continuous availability to Hadoop clusters, both in the LAN and across the LAN. One of the most important points here is this is an active technology. So when we start talking about Hadoop and multiple clusters, there's a couple of issues around that. You need 24/7 availability. You need consistency, which is a difficult problem, and it comes with complexity, a lot of complexity, especially if you start talking more than 2 clusters. How do you coordinate data between n number of clusters? We do talk to a few companies who are running 3 or 4 clusters, and they want to be able to do global analysis and other global log analysis, or stream analysis, whatever the mechanism is. And once you get past 2 data centers, how do you do that? So what does it mean for Hadoop to be enterprise ready? Well, first of all, you need to high up 100% up. This is related to SLAs for the business. This is related to regulatory compliance in certain spaces, if you're financials, healthcare, other systems. HDFS has to be deployed globally. Your data centers need to be able to access your data, and it has to be consistent everywhere. And one of the things that we need to use the administrative burden. We can't make this more difficult than current mechanisms. And we have to simplify disaster recovery and reduce your RTO, RPO nodes. This is all related to what makes things enterprise capable. And of course, the other thing that we add to this is you need to be able to maximize the utilization of your resources, both within a single data center and across data centers. This is one of the weaknesses, typically, of the traditional multiple data center setup. So moving away from the world of today, the world today is active passive. If you're looking within HDFS, you have a single name node with just one standby. So this is inefficient utilization of resources. You have one server that's just sitting idle, or one process, and then to support this extra idle process, you have multiple other processes, Quorum Journal Manager, Zookeeper nodes, which if you're not running HBase or some of the other technologies, you're not going to use typically. And you have the whole standby node itself. You still have the performance bottleneck of a single name node, even with a standby. If you have let's say 7 reads to every write, or a high utilization cluster, you'll actually start seeing, especially if the cluster grows, bottlenecks on large scale jobs. And with a single standby server, you're still tied to your beaver. When that primary active name node goes down, your standby comes up live. Well, now you've got a single point of failure. So now you need to go out and fix your single point of failure, and pretty much immediately. And one of the big things here is this is limited to LAN scope. We need to be across data centers. We need to be global. This is a LAN scope fix. So what does active bring to the table? We utilize all the resources. Only name nodes. You don't need QJM, you don't need Zookeeper. These are active name nodes, which are peer of each other. You can scale this out as the cluster grows. So let's say you start with 3 active name nodes. Let's say your cluster gets to be over 1,000 nodes. You decide you need to be either less of a bottleneck or more resilient to possible failures as your SLAs increase. Well, why don't you run more name nodes? We can do that with our technology. Load balancing. You have multiple name nodes servicing the same HDFS namespace. So instead of a single name node being a bottleneck with all the RPC traffic coming through there, you can now automatically round robin between multiple name nodes. So you don't have those traditional bottlenecks you do within a single name node system. And globally consistent. So what does global consistency mean? Well, to get to that point, let's talk about what it means to be active-passive with a standby data center. First of all, the biggest one, it's an idle resource. A lot of times your disaster recovery cluster is just sitting there idle. You're still ingesting data into a single data center, then copying it to the remote data center. It's typically disaster recovery only because all your synchronization technologies are a single way, whether it's DisCP or you're using any other formats. And this is error prone. DisCP is not 100% reliable. Clusters can diverge over time. And how do you scale beyond 2 data centers at this point? Do you have 2 active data centers that are trying to copy data without stomping on each other into a single disaster recovery? Do we now have 2 DR centers for each one of our Hadoop clusters? That's a lot of idle hardware, a lot of overhead. So what does active-active mean? Well, first of all, your disaster recovery resources now become available compute resources. You can ingest data at all of your data centers. You can run jobs in all of your data centers. We say both here, but that's really all. Replication is multi-directional. This is active-active. Each one of these data centers has active name nodes that can actively accept reads and writes, and then you can choose which blocks get replicated between the data centers. Absolutely consistent. You're no longer copying files from one data center to another data center. This is a single HDFS namespace. So we guarantee absolute consistency of your namespace, and of course, end data center support. This is actually something that we've solved this problem very well in the subversion space. Having multiple subversion servers, 3, 5 servers, where all of your developers are working on the same set of code, single copy consistency. We do the same thing with the HDFS name node. So you're now looking at globally consistent data across multiple data centers. So right now, the traditional way to approach HDFS and approach Hadoop is a single cluster. Let's take all our applications, our HBase, any real-time queries we're running, our large-scale MapReduce, let's put them all in one big pool. This is not the best use of your resources. You end up with data locality issues. Your network utilization is not optimized because you can't necessarily guarantee the jobs are running concurrently with the nodes where the data needs to be and where in the system. This is complicated. You now have to, are these nodes all being used by a region server and a node manager and a Spark process? So another approach that we see is, hey, let's make multiple clusters. Well, now we've just created the problem we saw again. We now have, how do we guarantee that the data in each cluster is the most up-to-date data it needs to be for our reporting? How do we actually efficiently use this resources? And what happens if one of these clusters is not available? So we say, make a single cluster, a single HDFS namespace, let's call it, but zone this cluster out so that you have one HDFS namespace consistent across all these systems, but the applications themselves run in their own kind of compute area clusters, their own native HDFS as opposed to in the global space. And now, this is where things get interesting, disaster recovery. And disaster recovery is one way to look at it, but really what we're enabling is not disaster recovery, we're enabling a global Hadoop cluster. So what comes with that is, first of all, you're only going to replicate the data within the namespace you want. You can choose which data stays native to the local cluster, which is tagged as global data to be replicated everywhere. Let's lower your TCO. You know, all those idle systems you had running for disaster recovery, now you can run jobs on them. You can ingest data in multiple data centers. You can use them to run different types of data. You can use heterogeneous hardware profiles. Your hardware does not have to be identical. So, talk a little bit about how multi-data center Hadoop happens today. I'll talk a little about our core technology and really dive a little deeper into the use cases. After that, I'm going to show you a short demo of the technology and take any questions from anybody. And if there's something that really just kind of blows you away about this or something you just don't understand, I'll be happy to go in depth once we finish up here. So, what's wrong today? there's two different approaches we see. Periodic synchronization of data and the multiple ingest through some sort of centralized splitter, like a load balancer or some type of system like that. So we start talking about periodic synchronization. Well, what is DISCP? It's a map reduce job. So you're using your cluster's compute resources in order to make sure that you're copying your DR center. It's not a great use of your resources. It's a read-only process, your data center, your disaster recovery data center. You don't want to copy data from the DISCP in your disaster recovery data center and also be writing locally to it. You don't know if there's going to be namespace collisions, you don't know if there's going to be block ID collisions. There's all sorts of difficulties with that. And over time, we've seen inconsistencies. We had a few of our senior engineers come from eBay, PayPal, and larger companies, and over time they discovered that these diverge. Not immediately, it takes time, but if there's any sort of hiccup in between the data centers, you guarantee the blocks get all the way across. You end up turning off the CRC checking after a while because the sheer amount of data you're trying to copy across means it's too resource heavy to actually do a data copy. And it's just not the most efficient use of network. Instead of using your bandwidth all the time, you're running a periodic synchronization that's going to saturate your bandwidth between the data centers. And there's probably some QoS rules that you can't actually use all that data. And then, of course, parallel ingest has a whole other series of issues. First of all, any WAN hiccup between the ingester and the data center and this data is not going to get to both sides. You need to make sure you have a large buffer within this to make sure data can make it to both sides. And you've now generated a new single point of failure that's going to require more system administration attention, more time. And this is going to be great for streaming technologies like using Flume, but what if you're just copying large files at any given time? How's that going to work in this mechanism? And of course, if you create data on one cluster, how's it get to the other cluster? It doesn't work this way. So our core technology is something we call distributed coordination engine, or decode. It's our patented WAN-capable Paxos implementation. For those of you who are not aware of what Paxos is a distributed computing algorithm. It's a family of protocols for solving consensus in a network of unreliable processors. Computers on a WAN. Computers that can go up and down. Systems are by their nature unreliable, but this is a mathematically proven protocol from came out of actually some research in the 90s that's guaranteed consensus amongst a group of participants, even in unreliable situations. Our difference is there's no restrictions on your distance between the data centers. We are not time and latency dependent. You hear about other implementations of this protocol within Google, within Microsoft, within other companies. It's tied to specialized hardware, very much vector clocks, time synchronization, very tight. Our implementation is completely time independent. And this is not sandblock device replication. So you don't end up with the RTT timeout issues you do if you try to stretch traditional block replication across great distances. So this is truly, this could be a cluster in the East and West Coast, a cluster in the West Coast, a cluster in Europe. There is no sort of latency dependencies. Now, as for how the distributed coordination engine works, we're using an example here of 3 name nodes. This could be 5, this could be more. It's a fixed number of participants. Now, this fixed number of participants can be dynamically changed, and so later changes will happen with that new number of participants. But for right now, we're looking at 3. The majority of these systems have to agree for a change to happen in the namespace. So, let's say someone proposes a change ID. This could be, we're doing a deletion of a block, we're adding a file, we're doing whatever we are to the HDFS namespace. That change is immediately synchronized with all the name nodes and says, hey, do a majority of you agree that this is the next ID? If that proposal is accepted, it's granted, everybody writes it out. So instead of using clocks, we use what we call the global sequence node. So all transactions happen on all nodes in the same order. Now what happens when we lose a node? This could be for multiple reasons. This could be for hardware failure. This could be for network failure. Planned outage, unplanned outage. For whatever reason, we only have 2 out of the 3 name nodes available. Well, you know what? That's still a majority. So we can continue to propose changes, and because we're able to talk to majority, we can continue to get agreement and move the namespace forward. Now, as you've noticed, this global sequence number is advancing. on 2 of the nodes, but the third node, it's going nowhere. We don't know why this node's out. What happens when it comes back? Well, it comes back in. The first thing it does is tries to contact the majority. When it contacts the majority, it's going to find out what the current global sequence number is. There's 2 possibilities. The first one, depending on how far behind it is, it can just replay those transactions it missed and then come out of safe mode and start accepting writes again. And this is a completely automated process. And you can set how far back you want this to be depending on how much memory is in your name nodes, how busy your cluster is. You can say how many transactions you want this to be. The other case, of course, is we've completely lost the node. We need to rebuild this system. Well, one of the advantages here, you know what? We have 2 other replicas of that FS image. They're active systems. So let's go ahead and we know what global sequence number each of those FS images are at. Let's copy one of those to bring this node back up into a known state and a known global sequence, replay from there. So we can actually bring other name nodes back into the system without downtime on the remaining nodes. How does this actually look in the wild? It looks something like this. This is a 2 data center example here. Each of the data centers we've configured with 3 name nodes. All changes to the system that happen in kind of this order. A block write request comes in. These sort of change the HDFS namespace comes in. How do we do this? Well, we coordinate the metadata changes within the name node across all the name nodes. And this is a synchronous process. It's fairly fast. You see there's an even number of data centers here. We can designate one of these data centers as being the more important or primary data center and give it a distinguished node. Give one of the name nodes there an extra vote. And this is something you can rotate throughout the day depending on how your company's set up globally, what time each cluster is busy, depending on what time each system's busy. And so locally, you get land speed performance. Now, once we've coordinated the namespace, at that point, immediately, if you were in a second data center, you could do a HDFS, DFS, LS, and you could see the context because the namespace is consistent and it's very, very fast. Now the data has to get over there. So your client continues and writes a block into the local HDFS. It goes through the write pipeline, goes through whatever your replication factor you've set up is, and then it sends one of these blocks to whatever foreign data centers it needs to get to. At which point that block is then handled through the local write pipeline to whatever replication factor is set in that data center. So you can have data centers with different replication factors. This becomes important in one of the use cases I'll talk about shortly. But it also means your disaster recovery data center, if you want to actually treat this disaster recovery data center, you don't need the same amount of storage. Maybe you only want a replication factor of 2 there, and you want to reduce your storage needs by 30%. You can do that. So what are the use cases for this? First of all, eliminate the name node or the single bottleneck of one active name node. I don't know how often you see this in your clusters. We've talked to a few very large companies, and there's some times where they have jobs that before they, like let's say it's a large-scale Kafka ingest of a lot of log data. They want to be able to process that coming in before the next dump comes through. And that becomes very important that they'll actually be writing heavily enough that it blocks all RPC traffic and any other jobs can't run. Let's go ahead and talk about multi-data center ingest. Instead of having to send all your data to a single data center that might be across the country, ingest the data at or close to the location where it's being generated. Do any sort of pre-processing and summarizing of that data, and then only replicate the summarized data to do global analysis. Or depending on the volume of the ingest, maybe you can replicate all the data. But you can choose how much of this data you need to replicate, how much it will work with. And also, we talk about cluster zoning. So this is really interesting. You know what? But use the right resources for the right applications. You heterogeneous hardware profiles. You can have a single HDFS namespace with a lot of the traditional 2U, lots of disk systems you would see for large-scale data lakes, MapReduce jobs, that kind of thing. And then have another cluster that's replicated in the same HDFS namespace, but these are systems designed maybe for Spark jobs or in memory. Lots, maybe not a lot of disks locally, maybe you only have a replication factor of 1 there, but a lot of memory, a lot of CPU power for doing real-time query jobs. And then maximize your data center resource utilization. This one's easy. You can actively use both data centers. You can run MapReduce jobs, different jobs in the same data sets in both data centers. I'll be demonstrating that here in just a few minutes. And of course, from a disaster recovery standpoint, your data is as close to current as possible. These blocks are copied asynchronously as they're created. And one thing that's not mentioned here, and this is kind of important, with this CP, you do not know what you don't know. When that cluster comes back up, you don't know if there's any data you're missing. You don't know what's inconsistent from what's in the primary data center. This is a single global HDFS namespace. You know if there's any blocks you did not copy because you have a copy of the namespace. So from an auditing standpoint, in a disaster recovery situation, you know what you need to recreate. You know what's missing. You know what needs to be generated back in. And that can be very important when it comes to regulatory compliance, meeting any SLAs that your customers require. So talking a little bit more in depth about the heterogeneous hardware use case. Optimize your hardware for the job profile of what you want to run. Whether you're looking at batch jobs, real-time jobs, HBase, NoSQL type of jobs. Set up the hardware for the type of job you want to run on it, and then span the HDFS namespace across these multiple clusters. And then you only have to replicate the data that needs to be used for each job to the appropriate subcluster. Maybe you have one central cluster that's your true, this is the big MapReduce, this is my petabytes of data I'm ingesting, but you have a cluster with a replication factor on the side that's doing all your in-memory processing. And so it doesn't have to worry about I/O blocking because of all the writes happening in the cluster, any sort of work it's doing. It can just sit and crunch numbers wherever it needs to do. And this can work on a LAN scope, so it's next to each other, so it can pull blocks from that other data center immediately, almost no latency. Or this can work at a WAN scope. And once again, we have more than one name node per data center. No bottleneck, and we don't have to worry about losing a single name node at any given point in time, because there's another active name node still in operation. There's no sort of failover process. Another use case, subclusters. Isolate the dev and test clusters. But because they're in the same HDF namespace, you can now use a staging or a dev or a test cluster and test against real active live data. You're not having to copy another data set into a different data center to do tests. You can actually be looking at the same data, just writing to a different location within HDFS on your outputs. This is a great benefit as you actually want to do dev test on what you actually want to process. It takes some of the guesswork out. Okay, this is live. What's the data going to look like? And all through this course, we're guaranteeing the consistency of the data. It's especially the LAN scope, it's pretty much available immediately. Latency very small, high bandwidth. Or let's say your cluster is grown and your data center is partitioned. A lot of data centers are, right? So you'll have whatever you term a data division, a data hall, a room, where you have a single core switch that goes between the rooms. You don't want to span an HDFS cluster across this switch. Your network guys are going to screen you for the network traffic. They don't want to see all these block reports, all this replication going across. Well, set up two clusters. And the only things going between them is the name node metadata and any blocks that need to be replicated across. So it allows you to scale within a single data center where you might actually have to set up a secondary cluster or move the entire thing together. So I'm going to show you a quick demonstration. What I'll be doing is a real simple, just running a TeraGen TeraShort to generate data on one of the clusters. We'll have some graphs that are showing the RPC bytes in and out of the name nodes, just to get an idea what the graphical effects. And then another graph showing what we call the foreign blocks. The blocks that we expect to be in our local cluster that we know about in the namespace, but have not yet been copied across the WAN. And then on the other side, when we're done, we'll run a TeraValidate in the other data center. And you'll see that we can actually run two different jobs in the same set of data. Or generate data in one data center and then operate on it in another. All right, sorry this is going to be a little bit stretched out. So what we have here is two clusters we've generated in AWS. One of these is in the North Virginia availability zone. The other one is in the Oregon availability zone. So this is bi-coastal. And each of these clusters is configured with 3 name nodes. So what I'm going to do here in the Virginia side is I'm just going to do we have a script to run this. is I'm just going to simply run a TerraGen followed by a TerraSort. I'm not generating a lot of data. I don't want to stand here for 15 minutes while you guys just watch graphs move around. So what we're doing is we're just really quickly generating a few megabytes of data, and we're going to run a sort on it. And you can see that the RPC bytes in and out on the name nodes starts peaking immediately. Well, now what happens if I'm running this and I lose one of the name nodes? So what I've done is I've rebooted the third name node in the Virginia side, and you'll see the bytes in and out goes to nothing. There's no data coming in and out of that. Nothing happened to the job. I'm still seeing data running through here. Now this is not generating a lot of data, so you might actually not even see the form blocks come through, because this, even on a 1 second interval, these might be copying very fast. When we do the validate, it's usually when we do see the form blocks on the other side. But in the meantime, so this is in Virginia, I can come over here and look in the working directory. On the other side of my cluster in Oregon. And I can already see the in and out directories from this demo I just started on the other side of the country. The namespace is consistent, and that's pretty immediate. And you can also see, it tells me which one of the name nodes I'm using. I'm actually using name node 1, the one local to me. But I could just as easily run this again. Just run it multiple times. Eventually you'll see the other name nodes in the cluster will start responding. Mostly because 3 is down, and 2 is managing the actual block ID generation right now. 1's going to be doing most of the response. You see this other name node's come back up. I've done nothing. It's come back up. It's generating data. I could log into that node. And I can run my HDFS commands here. Let's look in a different directory. So I'll look across in the temp directory where we're generating temporary data for my jobs. But I just popped onto a name node that was just rebooted, came right back up live and operational within the cluster. So as you see, we've actually finished that job. So over here in Oregon, let's go ahead and validate that information. Let's run a Terra validate on that. So what this validate script does is runs the Terra validate against the data that was generated by the Terra sort in the Virginia data center. And while that's running, I would kill one of the name nodes in the Oregon data center while we're at it. We still have 5 other name nodes to work with. Yes, we do actually. So that will immediately spike down to 0, continue on. Now you see our validate's writing data to the disk, and you see the other data centers, oh, there's a foreign block there. It'll disappear here just within probably less than a minute. But it's like, oh, we've written data to the drive, everything's run through. As you see here from the commands, we're actually now running a series of ls commands against the cluster to make sure everything comes out fine. The validate worked. Everything got written out appropriately. And so what I've done is I've generated data in one data center, had it appear in another data center without me having to do any sort of process copies actively. In the meantime, main node's down, no problems with this. It's truly an active technology. And the namespace is global. In this case, we've actually configured these clusters so that the namespace is truly global. The entire, from root on down, is being replicated in these clusters. We could have chosen something different. We could have said, well, let's only replicate user demo, and let's not replicate the rest of the namespace. I could copy files to the temp, and they wouldn't appear. It would appear on one side because you'll still see the namespace, but the blocks wouldn't be there. You can see when I went to pull, and I was like, oh, that's an unreplicated file. And you can choose how that behavior works, whether you'd actually pull that data across the WAN if it was something that was forming your data center for reading, or whether, hey, that's not local and you can't approach that data. So if you actually have data locality rules, you can enforce those with this as well. Okay, I'm going to go back to our So, does anybody have any questions around our technology we'll talk about today? There's a microphone coming around somewhere here. He's up.
Thanks. So metadata I/O is strictly synchronous, right? Meaning that the file creation operations could be latency bound in the worst case, or
Well, they can be latency bound, but they will always happen in the same order, guaranteed. So it's completely data safe and consistent.
okay. So when one site requests a data block that has not yet been replicated, is it sort of like a hinted handoff scheme where the local name node says, go talk to this other guy for it, or does a selected data node proxy that file read, or what happens there?
Yes, it processes file request. And that's separate from the replication process. So you can pull the data immediately ahead of wherever that block was in the replication queue for something immediately.
Cool, thanks. Is there a specific failure mode in greater than 2 data center environment where, let's say you have a weird network partition? Is there any sort of weird quorum management?
No, so like let's say you have data centers A, B, and C, and there's a partition between data center A and C, but they can both talk to data center D, you're fine. There's no sort of, we've been using this technology for a while in a lot of these situations. We have some customers in our lab space who have 9 or 10 active locations talking. So, no, this is very resilient to things like network partitions, everything like that. At this point, I don't think I've ever seen anybody force a split in this situation.
Great, thank you.
Any other questions?
So between the two data centers, what kind of technology you are using to synchronize the data, basically between
So
the name nodes
uh,
as well as between the data nodes?
excuse me, can you repeat the last part there?
I mean, between the two data centers, you have the different name nodes, like 3 name nodes in East Coast and 3 name nodes on the West Coast. And then you have the data nodes too, under 3 name nodes, and then data nodes should be also there under Hadoop centers. So if you are writing on East Coast, so between the name nodes to name nodes, how you are synchronizing, or between the data nodes to data nodes, how you are synchronizing.
Okay, so the between the name nodes, this is what our distributed coordination does. We have what we call the decone platform, and what it does is it actually handles all the discussions of these global sequence numbers, proposing transactions. If you know any terminology around Paxos or screen computing, each of these nodes is a proposer and an acceptor and a learner. So every one of these nodes can propose a transaction to the consensus group, at which point it will go out to all the known acceptors, which by default is all your name nodes. As soon as it hears back from the majority of them, that global sequence number will be decided upon, at which point all the learners, which once again is all the name nodes, will learn of the transaction and that global sequence number in the correct order. And that's handled, the synchronous process is handled by our own writing layer. It's its own TCP protocol. Now, separately from that, the blocks are actually handled asynchronously by the standard HDFS write mechanisms. So a client is writing into the namespace. When it makes the write, that gets halted temporarily until it gets assigned a global sequence number, so the metadata can be replicated everywhere. And then the client finishes the standard HDFS write pipeline. It writes a block into the HDFS environment, which then gets handled by the block replicator, make sure that it gets however many replicas it needs. Now, what we've done is we've actually made a small extension on top of the data node as well, so it understands the higher level topology of the data center. So once it's finished its standard write pipeline for the local, your standard default 3-node pipeline, so you write to a node, another node in the same rack, a node in another rack. It then says, okay, this belongs, it looks at its topology information and replication factors for the selected replication system. It says, is this a global block or a native block? If it's a global block, it then writes it to any other data centers it's assigned to. Single block only, at which point that local HDFS write pipeline handles it. So this is HDFS is already good at block replication. We didn't want to have to rewrite this mechanism. So we piggyback on it.
So my other question is like, what are the network bandwidth you are using between the two data centers?
However, so the overhead on the name node of metadata synchronization is fairly small. Metadata is very small, and we're not, in our protocol, all our messages are very tiny. So bandwidth of there is a very small overhead. Your bandwidth between data centers is going to depend on how much of the namespace you're replicating, what your ingest rate is on each of the clusters. So if you have a lot of data streaming into each cluster, you're not necessarily going to want to replicate the entire namespace, because now you're doubling the bandwidth coming into the cluster. If you have that much data coming to one side and the whole same amount of data going across the wire, and you're trying to do that bidirectional. Which is why we talk about the selective replication, maybe like if you're doing global analysis, and just at the point where it matters, do some summarization MapReduce jobs or whatever you're working with, and then only replicate that summarized space. So you're only replicating the data that truly needs to be global, even though you're ingesting volumes of data. It also allows you to ingest less data on a per cluster basis, which means maybe you can actually do more transformations to that data before you need to replicate centrally, because it's no longer instead of having to deal with the data from an entire country, it's dealing with regional data set. Maybe you can get more in depth because you're saying compute resources are now approached to a smaller pool of data. Maybe you get more in depth analysis out of that before you start summarizing it for global analysis.
Thank you.
All right, any other questions?
This is basically, you said the plugin on top of Hadoop that you still use Hadoop like you normally would use it, but this is intercepting it in an inner layer.
Yes, it's a plug. It's a non-intrusive plugin. We're not modifying any of the core any core HDFS code, so that if you have any applications that are written already, you don't need to modify them to take advantage of this. Unless you have logic that copies data to the other data centers, which you just don't have to worry about now because that gets handled at the infrastructure level.
It sounds like one of the big benefits of the ingestion across multiple data centers is your consistency, where
Yeah, so you actually can't, multiple data center ingest in the current world, you can ingest into multiple data centers, but now what do you do with that data? You then have to have an external process that takes that data into another location to do any sort of summarizing. Whether you're then transferring it into a traditional ETL type of system, or whether you're transferring to another cluster, how do you do that consistently? How do you avoid namespace collisions? How do you avoid block ID issues? How do you guarantee that the data is actually making it there with the CP? In our case, we're actually a single HDFS namespace. There's no sort of questions about the integrity of the data. The metadata is everywhere. You can tell if it's a good block or not. You can tell if it's under-replicated or not.
Just one more question. When you do make a write, say getting 1 million writes a minute or whatever it is, each of those writes has to go submit the metadata and get an agreement on the sequence number between all of the new nodes?
Yes. Yes, it does. And this is something that we've been doing this technology for about 8 years now. This is something we've have pretty highly tuned and highly optimized. We can definitely do a very high transaction now.
Thank you.
Yeah.
How about I run a Sonos speaker? How do I do that?
To this guy right here.
Now we're having a raffle. You guys want to throw a little raffle ticket up front? I'm going to give it away in about 3 or 4 minutes. So upon closing today, you want to go over there, throw a little ticket. You got about a 1 in 30 shot of winning the speaker.
Yeah, we have some books and t-shirts as well. So, yeah. Who doesn't have a raffle ticket? Just hand out some.
All right. Well, I want to thank everybody for listening to me today. And if you have any further questions about technology, we'll have our contact information up there. Mark is our major WANDisco representative down here in the Los Angeles area and in Southern California. This part of the country in general. So if you talk to him, he can get you the right resources and answer any questions you have about our technology. Thank you very much.
Alright, we're going to start drafting of the speaker and the ports. Take the speaker. Now,
I think you're going to win. It's a really good question.
so we can get Alex to come and pick out the window for the Sonos speakers. Alex, would you be honest, please?
Nope. Try to put not through.
So we have a winner, 714542.
542.
542.
542.
542. Anyone? Alright, we're going to go to the next one. Going once? Nobody? Alright, the next one. 542? 542.
Arm wrestle the other guy.
Okay,
All right, we're going to the next one.
here's the next number.
714559.
559.
559.
All right.
Alright, we're going to go to the next one. So Mark's going to pick the next. We're going to give out O'Reilly book feedback control for computer systems.
530.
714530. Alright,
Congratulations.
Next one we have interactive data visualization for the web. Sam, come to be honest.
You gotta pick it.
Pick up.
Pick some snack to be back, I think.
And whoever wins this one can get a free Portland t-shirt. Double bonus.
714560.
4560.
714560.
Chicken dinner. There you go. Real large. Take the top first. That's the good thing. Real large. That's all.
We got some t-shirts to give away. So, who wants to pick one? 534, 714, 534.
You have a
medium?
medium? Medium?
Alright. But I'm going to pick one. Seven one four 528. 528. Anyone? 528. No. No one? Alright. 714543. 543.
Media?
So, number t-shirt
540.
540.
You didn't think you're going to win anything.
Small or medium? Small, large, small. Too small, you got two small t-shirts.
Small.
Alright, there you go.
It's definitely small.
Oops, sorry. Anyone else small? Anyone else small? You're a medium, right? Just got one.
Go switch it out. Do you want a small
Did you want a
instead?
small? You want to switch out? I'm not a good thrower, so might as well come.
Thanks. You done?
You got some more books. So we have some books out if you want, you can just come and pick it up.
All right, thanks, guys. Really appreciate it.
Thanks. What's up, everyone? Very good. Let's start this one. Yep.
You guys always host here? Do they always host here?
Not always. It's
Nice place, though.